Our first speaker of this session is going to be Peter Boyle, joining us for Brookhaven National Laboratory. So he's doing great work bringing HPC to the world of particle physics. He's going to talk to us about his recent paper that I just saw in Archive. So Peter, thanks for joining us. Take it away.
Thank you very much for the invitation to speak, and thank you very much for working with me in our SIDAC project. So I'm going to discuss a paper that I put out last September as part of our SIDAC project. The interesting sort of generalization beyond particle physics, which is obviously the domain that I'm specifically working in, is the use of multigrid on multiple right-hand side systems, whereby in using multiple right-hand sides at the same time, the problem that you normally get of Amdahl slowing down of the coarse grids, right, they end up with small grids and very small amounts of work to do. You can increase the amount of work to do on the coarse grids, and in fact, in our particular case, promote matrix vector operations to matrix operations, which perform very well in GPUs. I'm secondly going to advertise the combination of preconditioned CG with block CG to make a preconditioned block CG, which is very natural then to apply with a multigrid preconditioner to many right-hand sides at the same time and give an algorithmic speedup in addition to the arithmetic intensity speedup. And I'll demonstrate that in our particular case, at least, we got a 20x speedup with the overall algorithm that we introduced. Our SIDAC 5 project I've got to advertise. There's 12 institutions, 2 of which are PETSc, principal homes of PETSc. Thanks, guys. We have weekly meetings, which are an absolute blast to take part in. I thank you both and Joe for your time in these, with a considerable amount of time being invested in this, and it's a great environment to work in. Why are we doing this? Well, one example of the importance of what we're doing in broader physics is the calculation. So the most precisely measured quantities known to man in terms of experimental endeavors have been the anomalous magnetic moments of the muon and the electron. Because the muon is more massive, it's more likely to be sensitive to new scales of physics than the electron. The muon G-2 experiment at Fermilab is the only large-scale significant high-energy physics experiment presently active in the US. Obviously, CERN is a bigger experiment than this, and the US is taking full part in CERN. But this is important to the US domestic experimental program. The accuracy that it produces at 10 to the minus 10 is equivalent to counting all the humans on the planet and spotting a missing child, right? Accurately, right? So this is immensely precise experimentation, which can be sensitive to new physics coming in. We have to compute what is the standard model prediction for this. That includes at several loops the hadronic vacuum polarization contribution, where a photon correction radiated off the muon and reabsorbed internally emits hadrons and reabsorbs them as a loop correction. And we have to try and calculate this to say this is a standard model prediction for the muon G-2 and compare this at this scale of accuracy to the experiment and look for a deviation with the hope that we discover new physics, right? And you can see in this, from the press release, this new experimental theoretical approach, lattice gauge theory in 2020, indicated that actually muon G-2 is consistent with the standard model. There's a paper coming out next week which completely solidifies this, where the power of computation is affecting the interpretation of this experiment as to whether or not it is consistent with the standard model and whether or not there may be new physics. A 4 sigma tension has been reduced to essentially a 0 sigma tension by the power of computing, right? And that is kind of an important impact and is affecting the conclusions of a major experiment. Okay, what we're doing? We're doing Euclidean gauge theory. What we're doing is numerical evaluation of the Euclidean path integral for QCD. So we have an integral over gluon configurations, and we work out the expectation values of various correlation functions, in this case the hadronic vacuum polarization correlation function, under an integral over all possible gluon configurations. We are typically dealing with something like 40 billion degrees of freedom, so it's a 40 billion dimensional integral. Fortunately, there's an exponential in there, so only a relatively small part of the space is actually significantly contributing, and we do it with Markov chain Monte Carlo to import and sample this integral, right? In fact, Markov chain Monte Carlo was invented in the DOE sphere of influence by high-energy theorists in order to calculate neutron populations and the things that go bang, right? So regardless, we're evaluating this path integral over all gluon configurations. Gluons are analogous to photons, quarks to electrons, and for the strong nuclear force. Inside this probability weight, we have a matrix inverse where M represents the Dirac equation, the Dirac differential operator. It's a hyperbolic PDE in Minkowski space. In Euclidean space, it's an elliptic PDE. The Dirac matrices are written implicitly. These physicists are terrible because we never write out our indices, right? So we just hide it to make the equations look simple. There are spin degrees of freedom that are just implicitly written in the Dirac equation and not actually discussed, right? But these gammas are 4x4 spin matrices. They're the generalization of the Pauli matrices, the 2x2 quaternions to the 4x4 case, but they anticommute in the same way. The determinant of this Dirac operator enters a probability weight. It's estimated via this phi dagger, by a Gaussian integral phi dagger, m dagger m to -1 phi. That imposes Pauli statistics. It determines total antisymmetrization. One important idea here is that we have, dating back to the 60s, the Atiyah-Singer index theorem. We couple our fermions to a gauge field, right? If the gauge field has a topological structure, then the Atiyah-Singer index theorem says that we induce zero modes of the Dirac operator, right? So the ill-conditioned nature of we will have ill-conditioned matrices as a result of this and the point is that this is a feature, not a bug, right? Topological non-trivial gauge configurations will exist. We're deliberately integrating over them all, and they will induce near zero modes of our Dirac operator, protected only by the quark mass, which will lift them above zero, right? But in order to get this, what we call anomaly physics correct, we actually have to have this represented in our system, and we're just going to have to deal with it somehow. And deflation is, of course, the way to deal with it. So you can see here an example of a configuration. I'm not going to explain. The left and right axes here are the eigenmode number of eigenvectors that we compute with our numerical Lanczos. The point is that we know by measurement that the gauge field had winding index number -2 on this configuration, and we had 2 unpaired modes, as Atiyah-Singer said there should be. If I set them quark mass to 0, these modes develop eigenvalues of 10 to the -13, so it's really a near numerical 0 when we've got the formulation correct, and they're only protected by the quark mass when it's non-zero. I have here, we're very proud of it, we've just started doing visualization of VTK and things like that, plugging it in quite nicely. This is the biggest ever configuration, I think. I think this is probably the biggest configuration that's ever been visualized in our field. Yep.
Is it near zero, or is it zero in exact arithmetic?
It's near zero because we have a finite extent of this fifth dimension that we introduce.
Okay.
So we're regulating, we could drive it to zero.
Okay, so it is actually almost zero, but it is.
It's almost zero, yeah. Okay, so we introduced, after years, decades of a no-go theorem that said that we couldn't have chiral symmetry in the lattice, it was actually discovered how to have chiral symmetry on our discretization. The famous Nielsen-Mia no-go theorem was evaded by introducing a fictitious fifth dimension. So we have this gamma 5 matrix times the hopping parameter, the derivative in the fifth dimension. What this does then is if you introduce a domain wall where you've got a negative mass somewhere, a boundary, and then positive mass somewhere, and you flip sign, then if you can basically, this is separable, you can ignore the spatial part. For each momentum mode in the field, you can introduce positive and negative chirality. Chirality is multiplying by gamma 5 solutions. And then in this fifth dimension, the derivative in the fifth dimension is solved with an exponential at this boundary where the positive chirality is bound and has a normalizable mode, and there's no normalizable mode for the opposite guy who flips sign in the other way, and you would have growing exponentials instead of falling exponentials. So this is similar to the trick used in topologically preserved quantum qubits, only they have a zero-dimensional qubit. We have a four-dimensional physical field bound in this perpendicular dimension, right? But they talk about these Majorana qubits. We've been simulating these for a couple of decades now with the 4D case here in our high-energy physics. The other thing about the system that we're solving is that we actually have a spectrum that encloses the origin in the complex plane in our matrix. And as we take the volume of our lattices bigger and bigger and bigger, it's like in Fourier mode, you get denser and denser n pi upon L modes, they fill in as you take the infinite volume limit. The spectrum will become very, very dense as you get bigger and bigger and bigger, with the result that you'll have a contour living entirely within the domain of the spectrum that encloses 0. And if you use a Krylov solver that produces a polynomial of the matrix, right, you will have a contour within the domain of the spectrum where the polynomial will always give you an integral of 0 because it's analytic, holomorphic, but the 1 over z that you're trying to approximate when you're inverting the matrix has to give you 2 pi I, right? Therefore, Krylov solvers will always have difficulty. This tends to get encoded in numerical analysis. There's a paper by Trefethen et al. About when do non-symmetric iterations work, etc., or how fast are non-symmetric iterations, or something like that. I can't remember the title of the paper. But basically, they talk about the half-plane condition. All the eigenvalues have to be enclosed in the half-plane of the complex plane. The fundamental reason, I think, is basically, if you're in this situation, you end up having to have a polynomial of order the rank of the matrix in order to satisfy this, right? And we obviously don't want that result because we have 10 billion degrees of freedom, right? We have a great collaboration with Matt, Mark, and Joe. We've invested in our software framework to enable research as a joint effort across the team. Our matrices are in the PETSc code. They're available for R&D. I think one of the goals is to expose these matrices, which have fairly unique properties compared to the rest of engineering and applied math, etc., to the applied math community. I think this is a long-term benefit to us to be able to have this in a framework that people can work on rather than a closed source or framework that people don't tend to have access to. We've been able to test all of the non-Hermitian solvers in PETSc against the main wall matrices. As I said, generally, we had a general expectation that they would not work. They did not work, right? It's nice that our mathematical knowledge is being verified. But expanded our knowledge, we could show it. We're actively pursuing various ideas, spectral transformation to precondition the matrix in a different way that doesn't have this half-plane condition, gauge fixing and local averaging, Buffalo are pursuing. I can't emphasize how productive and fertile the ideas being thrown around in our Zoom calls are. It's a wonderful research connection, and thank you. So, as we said, we have various cases. This is when we apply this preconditioning to avoid the wrapping in the complex plane issue, we can solve, but that has additional costs, and we're trying to then implement, or actually have implemented a multigrid based on this preconditioned matrix. And Joe was able to produce the spectrum in the complex plane of this operator, something that we don't have in our code, so the Krylov Shure was, in SLEPC was really useful. We found a bug. So this is, just a sign of collaboration with QCD and PETSc. We have a PETSc grid interface that I had in GitHub. We found a bug in FFTW for d equals 4, which is kind of entertaining. Okay, so statement that we were in the infinite volume limit and we had a dense spectrum. I've compared a 48 cubed by 96 solve history to a 96 cubed by 192 solve history with the same physics parameters. Changing the volume 16x did not change the convergence one bit, right? These are lying over the top of each other. The reason is that the convergence of a Krylov solver is a function of the spectrum only because it's making a polynomial approximation to the inverse of the matrix over the range of that spectrum. When you're in a sufficiently large volume, that spectrum is dense. There's something like 10 to the 10 eigenvalues that we're approximating 1 over z over its range, and something like 26,000 order polynomial. And basically, the Chebyshev bound gets saturated when the eigenvalues are sufficiently dense in any case. It's just you hit the worst case bound and you converge. And you can see that we can actually measure the lowest eigenvalue in effect out of the CG convergence rate, and it's correct. It matches what we get with Lantros to 6 significant figures, right? Which is quite something, right? So we understand the convergence rates. We understand it's going to be bad for the Krylov solvers. The right way to do this is with a multi-level algorithm, right, where you remove the low-lying eigenvalues from the problem as much as possible. There has been a history of lattice multigrid algorithms. Basically, the idea is that you learn the near null space of the Dirac matrix 1. You do that by producing order 60 or 30 algebraically smooth vectors, so near null vectors of the operator. You can do that with various filtering methods of polynomials of the operator or inverse iteration and things like that. This is non-trivial negation. We don't know them before we begin because phase is locally defined, right? So, the wave function of Fermi and the Schrodinger wave function, the phases are unobservable, right? In a gauge theory, it's locally defined and unobservable, so how do you locally average when you don't know whether to add or subtract, right? So the result of that is you use a covariant process to determine these near null vectors in whatever gauge the fermion is in, and then chop these into a local wavelet basis. You chop these phi k vectors into block vectors with disjoint hypercuboid blocks, and use these inner products with these local vectors to define the local averaging, right? We then calculate an approximate representation of the Dirac operator via its matrix elements between these blocked vectors phi k. One important observation by Lucier is that all the near null vectors are locally similar but globally different. So you can imagine that locally a near zero vector of the first order derivative is a constant vector. Globally, you might have some overall phase wrapping that's slow, right? With the result that you can relatively well approximate, say, a sine wave, the first violin string mode with a piecewise constant piece, and this generalizes to 4D and all of our gauge degrees of freedom, etc. Right? And that's basically the idea. And you would look at this and say, well, we can locally be fairly approximate in the infrared behavior here. If only you could file off these edges, so you would introduce a multigrid smoother, etc. And having taken this coarse grid approximation, had this Franken-stitched approximation to the infrared behavior, you could then post-smooth it and end up with a decent multigrid coming out of this. Okay, why? And one key thing is that we take all these inner products, so representing the coarse matrix here as the inner product of our fine matrix between these block vectors. We tabulate all of these in a big table of coefficients for the coarse grid operator. That if the k, the number of basis vectors is large, these are proportional to the number of basis vectors squared, and these will dominate the coarse operations, loading these coefficients from memory, which is why designing for multiple right-hand sides becomes sensible, because you can apply these large matrices A to multiple vectors for the cost of loading these coefficients. These A's are proportional to the number of basis vectors squared. These psi's are proportional to the number of basis vectors rather than squared to the power of 1. And therefore, you can load 4 of them or 8 of them or 16 of them for the cost of applying the matrix once to one of them, in effect, right? Saving the memory bandwidth. Okay, so we implemented this, what I call HDCG, but it's basically a multi-grid, multi-right-hand side multi-grid for based on CG iterations, a squared operator. And we, in the end, had this factor of 20 gain. This is the two volumes, 96 cube and 48 cube, both of which have the algorithmic gain demonstrated. And you can see both the fine grid and the coarse grid, in fact, have almost the same convergence history. So we've eliminated our previous method that we were using for our analysis was generating thousands of eigenvectors with Lanczos and deflating. That's a volume squared algorithm. This is an order volume algorithm, so we've eliminated the volume squared scaling of our problem in this, which is a significant outcome, right? It's asymptotically improved, right? So we've order volume, not volume squared. As part of this, we introduced a preconditioned block CG. So we took block CG RQ, preconditioned CG, went back to the original derivations of preconditioned CG and propagated through the proof. Fairly obvious. It's not particularly, why do people never put this together? Well, the proof was in a conference proceedings and kind of got lost in the midst of time, as far as I can tell. It's in sad, but yeah. So anyway, it's kind of neat, right, to take a little bit of an algorithmic step. And, overall, there's another sort of 30% gain that we could get from the preconditioned block CG over just the two-level algorithm in isolation, right? And that's seen with the kind of block CG tends to have this kind of superlinear convergence where it's no longer linear on a logarithmic scale. You can see the downward curvature. Okay, so overall, on one of our real test case systems, we had a 20x speed up, which is very useful to us. I want to advertise, we're doing CG, it's a Hermitian positive definite matrix. we are able to apply bandpass filters using Chebyshev polynomials and look at the power spectrum. I think of this as like a 1980s hi-fi Iowa, Sony, whatever, with graphic equalizer bars that dance up and down. And we're able to work out the power spectrum of different vectors in a multigrid. So the coarse grid correction is, of course, low mode dominated. So it's dominated by the lowest two bins. The post-smoother, the error is in this bin because the smoother is active and pulling down this bin and moving power into that bin, for example, and so on. So you can actually visualize using the operator and Chebyshev polynomials a power spectra, which are quite nice. So we've got, instead of the Fourier transform, we have the Dirac transform in this case, right? But it would work with any HPD matrix. Okay, something on performance. So we implemented our coarse operator in this in the end using these batched BLAS calls that exist in GPUs. These are nice because you can put in a whole load of work rather than a single gem to the GPU at the same time. And they also take pointer lists. So the issue of rearranging data and so on isn't required because you can give an arbitrary list of pointers to the interface, right? So it's wonderful to promote the BLAS interface to having pointers. I was thinking the earlier talk that if you had pointers for the columns, you wouldn't have to care about the time history, for example, right? I'd be talking to NVIDIA and to AMD and trying to get them to give you an alternate BLAS interface that lets you do the indexing through pointers for all of the columns within a matrix rather than having to worry about reordering data, for example. So our find to coarse to find coarse operator are all done with pointers. The hopping term in the coarse dimension is being done here by pre-computing a pointer list and putting the data into arrays with pre-computed pointer lists within these, right? So this is wonderful because we can do the coarse operator with single batch gem calls, and it does a whole lot, right? Entirely in BLAS. So we get great performance across a range of nodes. This goes up to 100. This is teraflops per node, and it goes up to 120 in cases, right? This is outrageous from my perspective, right? So these interfaces really work. The coarse operator used to be this thing that didn't have enough work in it. It was really hard to make it scale, etc. Put in enough right-hand sides and enough work, and the thing rips, right? That's fantastic. It's no longer the problem. Okay, so some profiles. You can see conjugate gradients on the fine grid is sort of d/d/d/ linear combination reduction, d/d. It's dense, it's boring, it's just repetitive, right? The multi-right side multigrid has a polynomial smoother that looks very like the CG sequence, and then a coarse grid correction. So we've got project to coarse grid correction with an iterative solve, and then coarse to fine again. And I think there's a bunch of deflation things being done somewhere in this, right? So regardless, the point is it's dense. Oh, the other thing that's worth saying is that the AMD tool is quite nice because it shows the standard kernels and the gem hardware specific kernels in different rows. So you can see that we're using the gem hardware all the way across the coarse solves here, right? So we really are using the tensor units, and it's shown by the profiler. There's 81 point stencil in the core space. We're doing it as 9 batches of 9, collecting 9 vectors and then summing them at the end. So you can see 1, 2, 3, 9 of these as dense calls, but even the coarse operator, as I said, is densely using and filling the GPU. So we've eliminated this latency problem you would hit with a coarse grid because we blew up the size of the core space. This is just bragging a bit about scalability of our fine matrix. We've got decent performance across a range of nodes. These are all, Perlmutter, Frontier, Aurora type nodes, and so on. Just a little profile bragging on NVIDIA A100 type nodes with the typical EDR 200 gigabit interface. We have face gather, start these communicating. While these are communicating, we can currently do the interior computation of all the terms that are locally corrected in our stencil. These overlap perfectly, and actually in this 32 to the 4th volume take the same amount of time with each other, so there's no loss to communication. Complete that, add the exterior with a second kernel call, and repeat, right? So we have this kind of poetry in motion where we're running the network and doing local compute concurrently. On Aurora, it was a little bit entertaining. It scales well. It's got lots of network hardware, but they had this pipeline mode, which at least we were advised was buggy and took some work, etc. In the end, we're doing our own form of pipelining where we have face gathers on the GPU, device-to-host transfers, host-to-host MPI being started as these complete with various polling things to trigger things running in the network concurrently. Then start the local intranode copies over the sickle mem copy, CUDA mem copy over the interior network, start the local kernel, watch MPI packets arriving, and in the order that they complete by polling, start stuffing these from the host memory to the device memory on the reception side, complete the local calculation, by which point this is all finished in the transfers, right? And then add the exterior again. So this is basically, we are shunting stuff device to host, host to host, host to device on the far side, but actually getting very good overlap as a result. A lot of work, some of which is working around bugs. We found a bug on the MPI on Aurora where GPU to GPU transfers intranode were being performed incorrectly because it was caching pointers that it shouldn't in a complicated way. You can ask me offline. Okay, so in summary, 20x speed up is transformational for us, needed for these G-2 calculations. We actually generated a simulation which was 16 times bigger than anything we've done before. We would have needed a 256 times bigger memory storage because of volume squared. We had to develop an algorithm to order, and we did. New precondition block CG solver, PBCGRQ. It's a natural partner to multigrid and Hermitian problems for multiple right-hand sides, in my view. This changes the nature of our problem. We've actually changed our physics simulation plans for various reasons because of this, the existence of this. We're doing, I think, good cutting-edge ASCAR relevant work here. It's really, HPC, advanced HPC in this. We contributed tests for the correctness, so our reproduced test, we insist on bitwise reproducibility, including reductions, etc. Intel and Argonne were running our code on the full system because we were finding bugs in hardware that the LinPack could not, right? We also found a bug in MPitch when using GPU memory in Aurora, which was fixed recently, but it would give incorrect answers for people doing GPU to GPU intranode if you were not careful for the last 6 months. I warn you all. Check. It was deterministic, so if your code gives the answer right once, it will give the answer right all the time, but check carefully. We're various forward-going projects, which I could go on about, but I think that's quite enough. So that's it for me.
Questions?
Very interesting work. So have you investigated the impact of precision? So I'm asking because I have done similar work using block file solvers for training neural networks. And it works beautifully in double precision. But if I do everything in single precision, which is the standard of machine learning, the block solver breaks down very easily. So my experience that block solvers are very sensitive to precision or noises. Another issue that I noticed that it seems that you are using tensor acceleration on GPUs. Usually these operations are done in lower precision, even lower than single precision.
Some of them are,
a concern, for your algorithm.
So in a multigrid, we typically solve the coarse grid to 10 to the minus 2 and solve the smoother is kind of converging to 10 to the minus 2 type accuracy as well. What we do a mixed precision approach where the outer is double and the inner is either 32-bit or 16-bit arithmetic, right? So basically the multigrid preconditioner is done in reduced precision, but the outer iteration, and the block solver lives in the outer iteration, right? And cross-fertilizes, so you do the multigrid correction step for all of the directions, all of the blocks, and then you do the dense arithmetic and double and the linear combination double for the outer portion. So we're doing mixed precision rather than simply flat precision. Any multigrid where if you're in the core solve only going to 10 to the minus 2, it cannot be sensitive to 10 to the minus 3 scale perturbations that you get from FP16. But you have to recompute the residual in the outer solve exactly in double, or even better if we had it, and then propagate that through the BCG-RQ. BCG does have this problem of the rank deficiency developing. And there's a few papers, but I haven't seen any great theoretical analysis that I understand to say which matrices will it work well for and which will it not. It seems to be a kind of try it. Sometimes it works, sometimes it doesn't. Because you need the subspaces need to be cross-talking enough for the different solves that they have productive sharing between the different search directions, but not be so similar that they end up being rank deficient and parallel to each other. And the theory of how that being close enough in directions to be useful, but not so close that they just lose rank. And but BCG-RQ at least is stable against this rank deficiency developing because it doesn't give you nans, it just gives you zeros, zeros that propagate and don't really add anything, if that makes sense.
Well, if we've got more questions, we can try to bring them offline. Let's thank our speaker one more time.